Hello and welcome. Camera calibration is essential for many high-precision applications. With MVTec HALCON, you can easily calibrate your camera setup. In this tutorial, we will briefly discuss some basics and background knowledge. Then, we will talk about the many details that can improve your calibration result. First, what is calibration used for? In image processing, we can get information like positions, distances, and lengths in pixels. Calibration allows us to convert this into metric information. Thus, we can measure objects in meters or remove lens distortions from images. For accurate results, a meticulous calibration is necessary. To keep the video introductory, we assume that you want to calibrate a setup with one camera using an MVTec calibration plate. As a result of calibration, you get internal and external camera parameters. Internal camera parameters describe the camera-specific parameters. External camera parameters describe the position and orientation of the world coordinate system relative to the camera. Each calibration plate comes with a description file. In this file, the centers of all the calibration marks are specified. During the calibration process, you acquire images of the calibration plate and locate the marks and their centers. The calibration then has to solve the equation that minimizes the distances between the marks in the images and the description file. Let's go through all the components and steps of this process to learn how to get optimal results. First of all, the camera and lens. HALCON includes many different camera models to be able to calibrate different hardware setups. This includes, for example, line scan cameras or tilt and telecentric lenses. Usually, the optical system you're using will introduce distortions to your images. HALCON can handle a wide variety of lenses. However, for high-precision applications, it can be helpful to use a high-quality industrial-grade lens. HALCON includes two distortion models. The division model uses one parameter to model radial distortions. The polynomial model uses 5 parameters to model radial and decentering distortions. Typically, the accuracy of the division model is sufficient for most applications. Additionally, working with the division model is usually faster. Also keep in mind that edge detection is much easier in grayscale images compared to RGB images. Thus, if your application doesn't require color information, but precise measurements, we highly recommend using a grayscale camera. Additionally, the aperture and focus of the lens must not be changed during or after the calibration. Use the locking screws if the lens has them. Any hardware changes require a new calibration of the internal and/or external camera parameters. For every calibration, initial internal camera parameters must be given. The initial values should be derived from the data sheets of the camera and lens used. These initial values are crucial for a successful calibration. For more information about initial values, have a look at the chapter Calibration in the operator reference. Next, let's talk about the number and variety of calibration images. For this type of calibration plate, we recommend at the very least 2 images with the plate flat and 4 images with the plate tilted. Tilting the plate is necessary to calibrate certain camera parameters. Try to diversify the orientation of the plate while covering the field of view and actually the whole 3D volume where measurements are intended homogeneously. As a rule of thumb, with regard to your final application, it's much better if you can interpolate later and don't have to extrapolate. Note that the polynomial distortion model is especially vulnerable in this regard. Consequently, an even better coverage of the field of view is necessary. Next, the calibration plate. For a precise calibration, the plate needs to be non-deformable, completely planar, and the positions of the calibration marks have to correspond to the values in the description file. You can obtain high-quality calibration plates from our local distributors. For more and up-to-date information about available sizes and accuracy, have a look on our website. Printing a calibration plate on paper, for example, is barely suitable for testing. It will almost never produce results with a sufficient accuracy for applications in practice. To find the suitable size for your setup, consider a plate that is roughly the size of your field of view. It's no problem if the plate is partially outside the image, only at least one finder pattern needs to be visible. As mentioned before, tilting the plate is important for a successful calibration. Depending on the physical space available in your setup, this might require a smaller calibration plate. Additionally, consider that the calibration marks should have a diameter of at least 20 pixels. This might require a larger calibration plate depending on your setup. With all this information, it should become clear that image quality is of the utmost importance. For a precise calibration, a good focus is important, in particular when tilting the calibration plate. A large depth of field is advantageous, but this of course also depends on the requirements of your application. The illumination should be homogeneous in your complete field of view. The contrast between the light and dark areas of the calibration plate should be at least 100 gray values. On the other hand, overexposure must be avoided, especially near the calibration marks. If the images are too dark, consider the following steps in this order. First, increase the illumination if possible. Then, consider increasing the exposure time if this does not lead to motion blur during calibration or in the real application. Additionally, you can increase the aperture to let in more light. However, this decreases the depth of field, which might be undesirable for your calibration and application. Adding a gain on the software side is not recommended because the additional noise lowers the precision of edge detection. Note that you shouldn't pre-process calibration images. This falsifies the results. To be able to reproduce the calibration and identify potential problems, it's useful to save your calibration images. Make sure that you use an image format that can be saved lossless, like PNG. Finally, how can we check whether a calibration was successful? The first indication is the error returned by the operator calibrate cameras. This error is the root mean square of the back projection of the optimization. A value of 0.1 pixel indicates that the calibration was performed with a residual error of 1/10 pixel. Thus, you can expect to perform measurements with a sub-pixel accuracy of 1/10 pixel. If you follow the hints provided in this video, you should typically be able to reach such an accuracy with your setup. Additionally, the internal and external camera parameters should be plausible. This means that they should be close to the expected values from your physical setup. We also recommend performing some test measurements with objects with a well-known size. In this HDevelop example, we reproject the calibration mark contours and residuals back onto the image using the calibration data. Thus, you can check whether the HALCON camera model can model your setup. As you can see, a lot of details have to be considered when calibrating a camera setup. To support you, the HDevelop Calibration Assistant checks things like focus and illumination when acquiring images. The same functionality is available in this HDevelop example. The chapter Calibration in the HALCON operator reference contains a vast amount of information. If you encounter any problems, have a look there. Additionally, all the requirements regarding calibration images are listed there for a quick overview. This concludes this video. Thank you for watching.